So we had an introduction on phase equilibria, and we mentioned that usually for non-reactive systems, the number of components equals to the number of chemical species. Maybe just a bit. In the previous examples, we are looking at the number of the degrees of freedom within a system. Okay, so I think the issue was determination of, you needed number of components and number of phases within a given system for you to determine the degrees of freedom. So for non-reactive systems, the number of components is given by the number of chemical species. For reactive systems, the number of components, because now for reactive systems, it means there's a change in the composition because of the reactions. Maybe the reaction could be dissociation of the components. So therefore that affects the number of components of a particular system. So the number of components is the number of chemical species minus the number of independent reactions minus a restriction due to the condition for electron neutrality. So this is just a recap. The degree of freedom or variance is the number of variable factors such as temperature, pressure, or concentration, which must be specified in order to define the system. Okay, so we looked at different ways to determine the degrees of freedom, and for different systems, they would have different degrees of freedom. Now, where you have a system, for example, a system having one phase like water vapor, to define the state of this system completely, one has to specify both temperature and pressure. So two variables have to be specified. So therefore, for such a case, we say that it has 2 degrees of freedom, and we say that it is bivariant. Now, when two phases are in equilibrium, such as ice and water, the only temperature or pressure, so one variable needs to be defined for you to be able to describe this particular system. So the system has 1 degree of freedom, and we say that it is univariant or monovariant in certain cases. You can use that interchangeably. Now, if a system has 3 phases in equilibrium, such as ice, water, and water vapor present at a triple point, then there are no degrees of freedom. So what this means is that all the variables are fixed. If you change one, then you're changing the whole equilibrium. So this one, they don't have at this point, you don't have any degrees of freedom. So this type of system is referred to as invariant. Now, we mentioned that for you to determine the degrees of freedom, you use the phase rule to determine the number of the degrees of freedom, which is given by F. So this is given by C plus 2 minus P. Or this can also be written as F equals to C minus P plus 2. Okay, so that is the phase rule. So now, but there's a way you can determine the degrees of freedom of a given system without using the phase rule. But there are certain things you need to know for you to be able to do that. So, considering a gaseous system with one component and one phase. So in this case, F equals to C plus 2 minus P becomes, substitute for number of components is 1, and number of phases is 1. So you get the degrees of freedom as 2. Okay. Now, if we are to consider this without using the phase rule, there are certain considerations that you have to make. Now, for every homogeneous phase, there's an equation of state or a phase equation. So, for example, the phase equation here is given by, it's a function of pressure, temperature, and concentration. So that is an equation of state. Now, subtracting the number of equations of state from the total possible variables, we get the degrees of freedom. Okay, so essentially that is how you determine the degrees of freedom without using the phase rule. It is the total number of variables minus the number of equations of state. So in this case, the variables are P, T, and C. Okay, and the number of equations is 1, because we have this only one equation of state. That is the phase equation. So F is going to be given by 3 minus 1, that is equals to 2. So you get a similar result if you had like the one you got when you use the phase rule. Okay. Now let's consider another one. You have a one component, 2 phases system. For example, where you have water and water vapor. Okay. So this is a system where the two are in equilibrium. The 2 phases are in equilibrium. And it's a one component system because it consists of water. So using the phase rule, that is F equals to C plus 2 minus 1. So it is a one component system. So this is going to be equals to 1 plus 2. And it has 2 phases, so minus 2. So here you get 1 degree of freedom. Now, if we are to determine this degree of freedom without the phase rule, we have to consider that there are 2 phases in this system. So for each phase, there is an equation of state. So for 2 phases, that means you have 2 equations. So you have equation of state for the vapor phase and for the liquid phase. For the vapor phase, we can represent the equation of state as this one. And for the liquid phase of water, it can be represented by this. So here, CV and CL, these are the concentration of the components in the vapor and the liquid phase, respectively. Okay, so we have 2 equations of state. Remember, you have to determine the number of equations in that system and also the number of variables in that system. So far we have 2 equations. Now for each phase, we have F equals to 2. If you're to determine using the phase rule, for each phase, F equals to 2. But the whole system in which water and water vapors are in equilibrium at a definite temperature and pressure, we have another equation. So apart from the equations of state, we also have the chemical potential equation. Okay. So for the chemical potential equation, when you have two phases in equilibrium at constant temperature and pressure, the chemical potential of a given component in the two phases is the same. So this is the equation for chemical potential. So that is the chemical potential of water in the liquid phase equals to the chemical potential of water in the vapor phase. Okay, so this here represents the chemical potential equation. Now, if you look at the variables, we have pressure, temperature, the concentration in the liquid phase, and the concentration in the vapor phase. So here, this is a total of 4 possible variables. So to get the degrees of freedom, we say it is the total number of variables minus the total number of equations. So remember, we have said we have 4 number of variables. And the number of equations, we have the chemical potential equation, that is 1. And then we have 2 equations of the equations as a result of the 2 phases, equations of state. Okay, so we have 3 equations to describe the system. So we say the degrees of freedom is going to be given by 4 minus 3, so equals to 1. So here you get a similar result to the one that you would have gotten if you had used the phase rule. You can consider another system, excuse me, a system that has 1 component and 3 phases. Okay, so that is, for example, a system that consists of water, vapor, and ice in equilibrium. Now, if you use the phase rule, here you get the degrees of freedom equals to 0. Okay. Now, without the phase rule, let's consider the number of equations and number of variables that are in this system. And we can use those to determine the degrees of freedom. So here we have 3 phases. And for each phase, we have an equation of state. So for ice, this would be the equation of state. For liquid water, this would be the equation of state. And for vapor phase, this is the equation of state. So we have 3 equations of state for the 3 phases. Now, when the 3 phases coexist at a temperature and pressure, the chemical potential of a given component is the same in each phase. Okay. So what usually happens is, we have 2 equations essentially, because we have 3 phases. So the chemical potential of water in ice equals to chemical potential in the liquid phase. And the chemical potential in the liquid phase equals to the chemical potential in the vapor phase. So we have these 2 independent chemical potential equations. And we also have 3 equations of state that we have indicated above. These ones determine the equilibrium between the 3 phases. So in total, we have 5 equations of state. Now, when you consider the variables, remember pressure and temperature. This is 1, 2. And then we have the concentrations in the different phases. That is concentration in ice, concentration in the liquid phase, and concentration in the vapor phase. So we have also 5 variables. So the degrees of freedom is total number of variables minus total number of equations. So that will be 5 minus 5. So that is equals to, it also gives you equals to 0, similar to what you would have obtained if you had used the phase rule. That is F equals to C minus P plus 2, or C plus 2 minus P. Okay. Now, if you consider another system that consists of a homogeneous solution of sugar in water. So here, these are 2 component system. Huh? We have sugar and we have water. But then this is one phase. You're forming one phase. So because you have only one phase, then you have only one equation of state. So the equation of state is given by this. We have a defined temperature and pressure. And then we have a concentration of water and concentration of sugar. These are the variables. Okay. So this means that the total number of variables is 4. So to get the degrees of freedom, it's going to be total number of variables minus the number of equations. So that is 4 minus 1. This equals to 3. Okay. Now for systems we can also have systems that have 2 components and 2 phases. Now the phase equations are given by this. So here, this C1 prime is the concentration of component 1 in phase 1. And C1 double prime is the concentration of component 1 in phase 2. C2 prime is a concentration of component 2 in phase 1, and C2 double prime is the concentration of component 2 in the second phase. Okay. So here we have 2 equations of state. Now, because we have 2 phases, chemical potential for the first component, we also have chemical potential equations for each of the 2 components. So chemical potential for the first component in the 2 phases is given by this. The chemical potential of the first component in phase 1 equals to the chemical potential of that component in the second phase. And the same can also be written about the second component. So we have 2 chemical potential equations. So total number of equations, here we have 2 phase equations because we have 2 phases, and we have 2 chemical potential equations because we have 2 components, okay, in the 2 phases. So we have the total number of variables. We have 1 temperature, pressure, C1 prime, C2 prime, C1 double prime, and C2 double prime. So the possible variables is 6. That is 1, 2, 3, 4, 5, 6. Okay. And the total number of equations of state are 4. So F is going to be given by 6 minus 4, that is equals to 2. So you can check that one out against the using the phase rule. You also get a similar answer. Okay, so I think we have said what the phase rule is. That the phase rule is given by is F equals to C minus P plus 2. Just a second. But how do you end up with this expression? Let's see how we arrive at this, how you can deduce this phase rule. So consider a system that has P phases and C components. Now, for a one component system, there are as many concentration variables as the number of phases. Okay, so for example, if you have this one component system, if you have one phase, then you'll only have one concentration to describe the system, or one concentration variable. But if you have two phases, then you're going to have different concentration of that component in the two phases. If you have three phases, then you're going to have three concentrations, different concentration in the three phases. So there are as many concentration variables as the number of phases. So we can say that for each component, we have P concentration variables. So if you have more than one component, if you have C components, then we say that we have C times P concentration variables. Okay. Now, apart from the concentration variables, to describe a system, you also need pressure and temperature. So these are two external variables that you use to describe. So therefore, this makes the total number of variables to be the concentration variables plus the external variable. So that is Cp plus 2. So that's the total number of variables for this particular system. Now, the number of equations. For each phase, we have an equation of state. So for P phases, if you have P number of phases, then you're going to have P equations of state. Okay, so we want to determine the total number of equations. So for P phases, we have P equations of state. So that is, if you have one phase, then you have one equation of state. If you have two phases, you have two equations of state. If you have three phases, then you have three equations of state. Now, there are also chemical potential equations. Yeah. We saw that if you have two phases, then you're going to have one chemical potential equation, because it's equating a chemical potential equation equates the chemical potential of a component in one phase being equal to the other, the chemical potential in the other phase. So if you have two then you have one. If you have two phases, then you have one equation of chemical potential equation. If you have three phases, then you're going to have two chemical potential equations, and so on and so forth. So we can say that for P phases, we have P minus one chemical potential equations. And since there are C components for our given system, then we have C times P minus one chemical potential equations. Okay. So for each component, you have P minus one, and for C components, it's going to be C times P minus one chemical potential equations. So the total number of equations equals to the equations of state plus the chemical potential equations. So that is going to be P plus C into P minus one. Now, the degrees of freedom, as we have seen, is given by total number of variables minus total number of equations. The total number of variables we had said equals to CP plus 2. Then this minus total number of equations that we said is P plus C into P minus 1. Okay. So when you open the brackets here, you have CP plus 2 minus P minus CP plus C. So here, of course, the CP cancel out, and you end up with this equation. So CP cancel out. Here you end up with C minus P plus 2. And this now gives us the phase rule as deduced by J.W. Gibbs. Okay. So that is how you deduce the phase rule. Now, we also have, I think we have encountered the Clapeyron equation, and we can use this for the deduction of phase rule. Now consider that you have two phases, A and B, of the same substance in equilibrium. So you have one component in equilibrium with each other at constant temperature and pressure. So the condition for equilibrium, chemical potential in phase A equals to the chemical potential in phase B. Okay. Now, if the temperature is changed by a small proportion to T plus dt, the pressure also is going to change to P plus dP. Now, the chemical potential in the two phases is going to become mu A plus d mu A and mu B plus d mu B. So we can say for equilibrium that mu A plus d mu A equals to mu B plus d mu B. Okay. If we subtract this first equation here from this second equation, we get that d mu A equals to d mu B. Now, we had previously described or defined, I'm getting some noises, I don't know. Someone has joined us and is not muted. So we have described, we are saying that when you subtract these two equations, of course, these ones cancel out. That is mu A and mu B. So you end up with d mu A equals to d mu B. But we have defined d mu as v dp minus s dt. So d mu A equals to VA dp minus SA dt. So we have these symbols here. The V with this symbol here represents the molar volume, okay? And the S with this symbol here represents the molar entropy of this, in that particular phase. And then d mu B equals to VB dp minus SB dt. So if we equate these right-hand sides of these two, because the other two parts are left-hand sides are equal, so we get VA dp minus SA dt equals to VB dp minus SB dt. If we rearrange this, putting the like terms together, we get SB minus SA dt equals to VB minus VA dp. So this SB minus SA is delta S, or change in S, and VB minus VA is the change in V, or delta V, okay? So if that is the case, we come up with two expressions. So we are saying that this is delta V, this is delta S. So if that is the case, we come up with these two possible expressions. Either dt over dp equals to delta V over delta S, or dp over dt equals to delta S over delta V. Now this, if you remember, this is the Clapeyron equation, and it's very helpful in discussing equilibrium between two phases of a pure substance, as we're going to see shortly. Now, if you consider just a second. If we consider a solid liquid equilibrium, so here you're considering the transformation of 1 mole of a substance from the solid phase to the liquid phase. So the solid is turning to liquid. Now here, delta S from the Clapeyron equation, delta S is going to be molar entropy of the liquid, or the final phase, minus the molar entropy of the initial phase. So that is SL minus SS. So essentially here delta S is going to be delta S fusion, because that is the process that is taking place. And delta V is going to be the final molar volume minus the initial molar volume. So essentially you're talking about delta V fusion. Now at equilibrium temperature, the transformation is reversible, the transformation of solid to liquid phase. So therefore we can use this expression. We say delta S fusion is given by delta H fusion over T. Now the transformation from solid to liquid is always accompanied by absorption of heat. So usually the solid would absorb heat and then to turn to liquid. So delta H, because of that, delta H fusion is always a positive quantity, okay? And if that is the case, if delta H fusion is a positive quantity, then delta S fusion is also positive for this, but for this substance, okay? Or for a substance, any substance. Now the quantity delta V fusion, that is changing the molar volume, it can be positive or negative, depending on whether the density of the solid is greater or less than the liquid. So remember this, huh? We know that volume is given by mass over density. So when you're moving from solid to liquid, there are some substances where the density changes. So when the density changes, then there's a change in volume as well. So there are some substances when you're moving from solid to liquid, the solid is less dense compared to the liquid. So if that is the case, it means there is a reduction in the volume. So when you're considering delta V fusion for that particular substance, which is the final volume minus the initial volume, it's going to be a negative value, okay? Because the volume is decreasing, okay? For example, for substances like water, bismuth, and antimony, I think you can do this experiment with water. You can take a volume of, you can take a bottle, whatever kind of bottle, and you fill it with water. If you put it in a freezer, you notice that there's some expansion, and that happens. So when you're moving from solid to liquid, there's a decrease in the volume, okay? So for water, or bismuth or antimony, delta V fusion is negative, as the density of the solid phase is less than that of the liquid phase. So if delta V fusion is negative, what does that mean? Our expression, that is the Clapeyron equation, that is dP over dt equals to delta S over delta V. This part, if this delta V is negative, it means that this is going to be delta P, dP over dt is also going to be negative, which means that the slope of the line of between pressure and temperature is negative. So when you plot pressure against temperature for that particular system, you're going to get a slope like this one here. It's a negative slope. So here, this represents the, what do you call it, solid phase, and this is the liquid phase. So you're moving from solid to liquid. This represents the variation of pressure with, not of pressure, but of the melting point with pressure. So here we say that the melting point is lowered with increase in pressure. So as the pressure is increased, we have the melting point is lowered, okay? Because when you consider a pressure here and a pressure here, then you have two different melting points. Now, just a second. Now, for a substance like sulfur, the density of solid is greater than the density of the liquid. So what that means is that there's an increase in the volume. Huh? So delta V fusion is positive. And if it is positive, then dP over dt is going to be also positive. That is the slope of the line. dP over dt is going to be positive. So here we have this type of, when you plot pressure against temperature, you get this positive slope for this kind of substance. So what this means is that as you increase the temperature, the melting point also is increased. So as the pressure increases, the melting point also increases. Now, but when you take typical values of delta S fusion and delta V fusion, the slope dP over dt has a large value. Okay. So hence, the curve is almost vertical in both cases. So in both these two examples that I've given, because we have very large values for delta V, for dP over dt, then the slope is very steep. It's almost vertical, yeah, for the two cases. Now, when you consider that, in that case, we are considering the solid liquid system when you're moving from a solid to a liquid. But if you consider the liquid gas system at equilibrium, so here you're talking about vaporization. So delta S here is going to be Sg minus SL. Okay. So this equals to delta H vaporization over T. Now this one is always positive because you know that the entropy of a gas is so much larger than the entropy of a liquid. So this one is positive. Delta S is positive. And delta V equals to Vg minus VL. Vg, the volume of a gas, is also much larger than the volume of the liquid. So the delta V also is also always positive. So here we can say for the liquid gas system, dP over dt is all equals to positive for all substances. So the liquid gas equilibrium line always has a positive slope. Okay. When you take the typical values of delta S vap and delta H vap, the value of the slope is found to be much smaller than that of the liquid, solid liquid equilibrium. So while we said for the solid liquid equilibria, it's very steep, almost vertical. For the liquid gas equilibria, the line is much smaller. The slope is much smaller. Okay, so it would be more inclined compared to the solid liquid equilibrium line. Now, the intersection of the curves for SL, or from solid to liquid, the solid liquid and the liquid gas, there's a point where the two lines meet. Okay. Now, where they meet, corresponds to a temperature and pressure at which the solid, liquid, and gas all exist in equilibrium. We're going to see this shortly in an example. We're going to look at two phase equilibria for one component systems. So you're going to see how this works out. So a point where these two lines meet, the liquid gas equilibrium and the solid liquid equilibrium, is called the triple point, where you have the three phases, that is solid, liquid, and gas, existing in equilibrium. Now, we also have a solid gas equilibrium as well. This is where you have sublimation taking place. A solid so you're moving from the solid phase to the gaseous phase. Now here, delta S is given by Sg minus Ss. So here, this is called delta S sub for sublimation, equals to delta H sub over T. This one is always positive as well. And the delta V equals to Vg minus Vs. This is called delta V sub and is also always positive. So from the Clapeyron equation, we say that dP over dt for this solid gas equilibrium is always positive for all substances. Now the slope of the Sg curve is steeper at the triple point than the slope of the Lg curve. Okay. Now, we saw that the first rule is very important in terms of determining the degrees of freedom for a particular system, but it has some limitations in that it gives the number of the degrees of freedom, but it does not tell us how much and in what direction the system moves to achieve the set of equilibrium. Yeah. So for you to do that, of course, you need the study of chemical equilibria for you to be able to determine the direction towards equilibrium. So for example, when you have a system having ice, liquid, and vapor in equilibrium, if we change the temperature, the pressure will also change in order to achieve a new set of equilibrium. So we said for a triple point, there's 0 degrees of freedom. Yeah, that is where you have 3 phases. Then you have 0 degrees of freedom. That means the 2 variables, temperature and pressure, are both fixed. If you change one, the other one also has to change. Or if one changes, then the equilibrium has been destroyed. So the system, for it to move to another set of equilibrium, the other variable also has to change. So the first rule does not tell us how much the pressure will change. When the temperature has changed, pressure will also change. But it does not tell us how much the pressure will change and in what direction the system would be moving to achieve that new equilibrium. Now, we can apply the first rule for different component systems. We can talk about 1 component systems. We can talk about 2 component systems. Of course, we start with the simplest, move to the more complex. So for a 1 component system, where C equals to 1, so therefore, from the first rule, the degrees of freedom equals to 1 minus P plus 2. So that is the degree of freedom equals to 3 minus P. So the minimum number of phases of any system is 1. So from the above equation, the maximum value of degree of freedom for a one component system is 2, because the degree of freedom here is going to be F equals to 3 minus 1. So 2 is the maximum value of degree of freedom for a one component system. So to define a one component system, what this means is that you need 2 variables. So 2 variables must be specified for you to define a one component system. So that is temperature and pressure. Now here the concentration variable is not considered because the composition is always the same. We're talking about a one component system. For example, water. You don't have, for a system that consists of only water, you don't have to describe you don't have to consider the concentration of water in this case. Now, for 2 phases in equilibrium with each other, the degree of freedom equals to 1. So degree of freedom equals to C minus P plus 2. This is a one component system. So just a second. So here we're talking about F equals to C minus P plus 2. So if you have, this is a one component system, so this is 1 minus, so 2 phases plus 2. So the degree of freedom here is going to be equals to 1. What this means is that the system is monovariant. This is what we mean by a monovariant system. That is, one of the 2 variables is sufficient to define the system completely. You only need 1 variable. If you have 3 phases for this one component system, when the 3 phases are in equilibrium with each other, if you use the phase rule, you get the degree of freedom equals to 0. So in this case, we say that it is not necessary to specify any variable, and the system is non-variant, or it is invariant. It has 0 degrees of freedom. The maximum number of phases which can coexist in equilibrium in a one component system is 3. Maximum number of phases that can exist in equilibrium in a one component system is 3. The graphical representation of these facts is done by considering the temperature pressure diagram for this particular system. So we can consider a couple of systems here to illustrate the facts that we have just mentioned. The first system is the water system. This is a one component system. Water exists in 3 possible forms. That is ice, which is solid, water, which is the liquid, and water vapor. Now these 3 phases, they have the following equilibria are possible. We have 2-phase equilibria and we have 3-phase equilibria. So 2-phase equilibrium means that you can have two phases in equilibrium. You can have the solid and the liquid in equilibrium. You can have the solid and the vapor in equilibrium. And you can have the liquid and the vapor phases in equilibrium. In terms of the three-phase equilibria, we can have the solid, the liquid, and the vapor, the three phases, being in equilibrium. So this is what we call, we'll see, this is what we call the triple point, as mentioned earlier. So this is what we have here. This is, remember, this is pressure against temperature. Okay. So here we have these lines, these curves represent different they represent the variation of different pressures with temperature. So here we have the solid phase in this region. Here we have the liquid phase in this region. And here we have the vapor phase in this particular region. Okay. So along the curves, the system is monovariant. So along these lines, we say that the system is monovariant, meaning that it has 1 degree of freedom. So along this line, you have the solid and the liquid phase being in equilibrium here, along this line. These are different values of pressure and temperature. Along this line, we have the solid and the vapor being in equilibrium. Along this line here, that is OB, we have the liquid and the vapor being in equilibrium. And then we have this point here where the three lines meet, that is at point O. Here, we have the three phases at equilibrium. So we call this the triple point. So within, just a second. So within the single phase system, within the single phase, the system, we say that the system is bivariant. So there has 2 degrees of freedom. So we are talking about these regions within the phases, meaning that you can define two variables are needed for you to be able to describe that particular system at that point. The point O, as we have said, represents where the three curves are meeting. Here, the phases coexist in equilibrium, and the system is invariant. So the curve OA, that is this one here, curve OA, is called the sublimation curve of ice. And here we said at this point, the solid phase and the vapor phase are in equilibrium. The curve OB, just a second, the curve OB here is referred to as the vapor pressure curve or the vaporization curve. It extends to the critical temperature 374, so to 374 degrees Celsius here. Beyond that point, no liquid exists. So above this temperature, 374, the liquid does not exist. And the corresponding pressure is 220 atmospheres, which is what we have at this point here. The curve OC, that is OC, is the freezing point curve or the fusion curve. Just a second. Okay. So this is called the freezing point curve or the fusion curve. It tells how, essentially what it tells how the freezing temperature of ice varies with pressure in such a way that the two phases are in equilibrium. Okay. So this shows you how the freezing temperature varies with pressure. Now there's another curve in that diagram. It is this curve here. O from O to O prime. Okay, it is this dotted line. Now this dotted line is called the metastable curve, OO. This curve results if liquid water is supercooled below 0.0 or below 0.0. So by supercooling here, we are talking about, it means cooling the liquid below the freezing point without separation of the solid. So it's still in the liquid form, but it is below the freezing temperature. So that is what we mean by supercooling. So this metastable curve is obtained by extension. Essentially, we're extending this curve B, we're extending it below this point O. So the phases along O prime are water and vapor. So those are the two phases that are in equilibrium. But these are in what we call a metastable equilibrium. So they are very unstable. The supercooled liquid is unstable at these temperatures with respect to ice. And as soon as the equilibrium is disturbed, if we disturb the equilibrium by adding a small piece of ice, the supercooled liquid will immediately be converted to ice. The degree of freedom along this curve is 1. Now point O, which we described as being the point where the three phases are in equilibrium, is known as the triple point, where the three phases coexist, and it corresponds to the temperature 0.0075 degrees Celsius and the pressure 4.58 millimeters. Okay. So that is the water system now, which is an example of a one component system. We also have another example of a one component system is the sulfur system. So sulfur is interesting in that it has two crystalline forms. So there's the rhombic sulfur and there's the monoclinic sulfur. So when you have rhombic sulfur and then you start heating it, at a certain temperature, it is going to convert to monoclinic sulfur. So the temperature at which this happens is called the transition point. So this is, for example, if you're considering, so this plot of pressure against temperature for sulfur, it is, there are several phases that are involved here. We have this particular region here represents the region for rhombic sulfur, okay? This region here in between, that is BCF, this region represents the monoclinic sulfur phase, okay? And then we have this other region here, it is DCG. DCFG represents the liquid phase. And then the region below here represents the vapor phase for sulfur. Excuse me. So we said that at a transition temperature, that is 95.6 degrees, rhombic sulfur transitions to monoclinic sulfur. And then as you continue heating monoclinic sulfur, at a temperature 119 degrees Celsius, it starts melting now to form the liquid phase, okay? So when you are considering the sulfur system, when you're using the phase rule on these 4 phase equilibria, we're saying that we have 4 phases. If you consider the phase rule, which is F equals to C minus P plus 2. So here, if you put in, you have, it's a 1 component system, that is sulfur, minus, we have 4 phases, plus 2. Here you see that you have a degree of freedom of minus 1. So this shows that for a 1 component system, it is impossible to have 4 phases existing in equilibrium because we have a degree of freedom of minus 1, which is impossible. But for this system, it is possible to have 3 or less number of phases together. So that means you can have 3 phases being in equilibrium, but not the 4 phases being in equilibrium. So let's consider the curves for this sulfur system. We have the curve AB. Notice this one here. This curve AB here, notice this is a point where you have the rhombic sulfur being at equilibrium with the vapor, the sulfur vapor. So this is the sublimation curve of rhombic sulfur, and it gives the vapor pressure of rhombic sulfur at various temperatures. So the 2 phases at equilibrium along this curve, that is AB, are rhombic sulfur and the sulfur vapor. And here the system, you say the system is monovariant. Okay. Let's consider another curve, BC. That is this curve here, BC. So along this curve, we have the monoclinic sulfur being at equilibrium with the sulfur vapor. So essentially, this is the sublimation curve for monoclinic sulfur. And it gives the vapor pressure of monoclinic sulfur at various temperatures. So here we have this equilibrium being existent. That is monoclinic sulfur at equilibrium with the vapor sulfur. Consider another curve, CD. That is this line here, CD. So here you have the liquid sulfur being at equilibrium with the vapor, sulfur vapor. So essentially here, this is the vaporization curve. So this is the CD is the vapor pressure curve of liquid sulfur, and it gives the vapor pressure of liquid sulfur at different temperatures. The curve is stable up to 444.6 degrees Celsius. The two phases in equilibrium along the curve is liquid and vapor sulfur. And we say that at this line, the system is monovariant. Essentially, the system along the curves is monovariant. You can also consider the curve BF, which is the curve BF. So at this, here we have the rhombic sulfur being at equilibrium with the monoclinic sulfur within this region. So essentially, remember we said at this point, the rhombic sulfur transitions to monoclinic sulfur. So essentially, this line shows the variation of the transition point with the pressure. Okay. This is referred to as shows the effect of the transition point and is known as the transition curve. The two phases in equilibrium along this curve are rhombic sulfur and monoclinic sulfur. Okay. Let's consider another curve, CF. Is this curve, CF. So at this curve, we have the monoclinic sulfur being at equilibrium with liquid sulfur. So remember at this point, at 119 degrees Celsius, monoclinic sulfur begins to melt to give us liquid sulfur. So this line here shows the variation of the melting point of monoclinic sulfur with pressure. This CF represents the variation of the melting point of monoclinic sulfur with pressure and is known as the fusion curve of monoclinic sulfur. The monovariant equilibrium along this line is we have the monoclinic sulfur being in equilibrium with the liquid sulfur. And there's the line FG. Okay. The line FG here. So along here, notice this is we have the rhombic sulfur being at equilibrium with the liquid sulfur along this line FG. So this is known as the melting point or fusion curve of rhombic sulfur. And it shows the variation of the melting point of rhombic sulfur with pressure. The two phases in equilibrium along Fg are rhombic sulfur and liquid sulfur, and the system is monovariant along that line. Now, within the phase areas, the system is bivariant. Now, apart from having curves, we also have various triple points. Yeah. So notice here we have this point B, we have point C, and we have point F as the triple points. So these are points where three phases are in equilibrium. Point B, we have rhombic sulfur, monoclinic sulfur, and vapor phase being in equilibrium. Point C, we have monoclinic sulfur, liquid sulfur, and vapor sulfur being in equilibrium. Point F, we have rhombic sulfur, liquid sulfur, and monoclinic sulfur being at equilibrium. So point B, the transition temperature, 95.6 degrees Celsius, at which rhombic sulfur is transformed into monoclinic sulfur. The three phases that are coexisting in equilibrium at this point are rhombic sulfur, monoclinic sulfur, and vapor sulfur. Point C, it represents the melting point, that is 119 degrees Celsius of monoclinic sulfur. The three phases in equilibrium, we said here are monoclinic sulfur, liquid sulfur, and vapor sulfur. And then we have point F at the temperature 151 degrees Celsius. I think you're going to notice an anomaly in this in the diagram here, because as it is, this point does not look like it is at 151. But in real sense, if you check the diagram in the internet, it should have been something like this. Such that this point here, where point F is going to lie here, is going to be at 151 degrees Celsius. And the pressure is 1290 atmospheres. So this corresponds to the equilibrium between rhombic, monoclinic, and liquid sulfur. Now at these 3 points, the degrees of freedom equals to 0. And we say the system is invariant or no variable. What that means is that no variable can be altered without disturbing the equilibrium, since all triple points represents the existence of the three phases in equilibrium with each other. So when you're considering water, we had what we call the metastable equilibrium. So also in this sulfur system, we also have a metastable equilibrium or metastable equilibrium. These are indicated by dotted lines. Okay, just consider the dotted lines. We have these dotted lines here. There's a point E. So there's a curve BE, there's a curve EC, and there's a curve EF. Okay, so this represents the metastable equilibrium. Now, here, just as the case of the water system, it involves superheating and supercooling. So if rhombic sulfur is heated rapidly or superheated, it will pass above the transition point B along BE without change. And finally, it would melt to liquid sulfur at the point 114 degrees Celsius. So here we are saying, here, remember here we have rhombic sulfur. So at this point, if it is heated past this point, superheated past this point, then it's going to move beyond this point without changing phase. And then at this point E, which is at 114 degrees Celsius, it is going to melt, so to the liquid phase. Okay. So the curve BE, which is an extension of curve AB, represents the monovariant metastable equilibrium, where you have the rhombic sulfur being at equilibrium with the sulfur vapor. I'm going to be moving back and forth so that you can see this. So here, just a second, we have the rhombic sulfur and the vapor sulfur being at equilibrium along this line, BE. Okay. Now the line CE is obtained by supercooling liquid sulfur along the extension of DC to the point E. So CE, remember BE, you're talking about superheating. But now when you talk about CE, here you're talking about supercooling of the liquid sulfur. So this liquid sulfur is being supercooled to the point E. The line CE represents the monovariant metastable equilibrium between liquid sulfur and vapor sulfur. Now, since the two metastable curves BC and CE are intersecting each other at E, the point E represents the metastable invariant triple point, where you have rhombic sulfur, liquid sulfur, and vapor sulfur existing at equilibrium. Okay. Now the curve EF is called the rhombic melting metastable rhombic melting point curve, and it shows the variation of the melting point of metastable rhombic sulfur with pressure. That is the line EF, this one here. So remember, this is the point F is the melting point of rhombic sulfur. So EF shows the variation of the melting point of the metastable rhombic sulfur with pressure. So the curve EF is an extension of the stable GF line into the metastable range, and the two phases which are in metastable equilibria with each other along this curve are the rhombic sulfur and the liquid sulfur. Just take note here that here we are talking about this line FG was the line indicating equilibrium between rhombic sulfur and liquid sulfur. So this line has been extended into the metastable region. So in this metastable region here, it will still represent equilibrium between the rhombic sulfur and liquid sulfur. So we have other examples of one component systems. Phosphorus, carbon dioxide, benzophenone, helium, just to mention a few. These are systems you can take a look at to see how the phase equilibria behaves for these. But we just looked at a couple of them so that you are familiar with the phase equilibria for one component system.